how can ray diagrams be used to locate images produced by convex mirrors? So now it's going to be curved the other way, and the mirror is going to be on this side. Since the mirror is curved the other way, the center of curvature, the center of the circle that would be made, is on the other side. And just like before, the focal point is right between the center of curvature and the mirror on the principal axis. But it's different this time because it's a virtual focal point. And if you draw parallel light rays in, like before, parallel to the principal axis, each one will obey the law of reflection. But notice the normal lines now, I'll just draw one. Like, look, the normal line would be going up like that. So this time, the light ray is going to bend up. But again, watch what I do here. It bends up as if it came from the focal point. So this time the light rays coming in parallel hit the mirror. Each ray obeys the law of reflection, and when it hits the mirror, it reflects as if it came from the focal point. Did it really come from the focal point? No, there really isn't any light behind the mirror, but it's as if all of those rays are coming . Notice the convex mirror. All the light rays spread apart. So it's also known as a diverging mirror. because all the light rays diverge when they reflect off of it. This focal point over here is called a virtual focal point because there really isn't any light there. If you put a little piece of paper there, you're not going to start it on fire. It's just that all the rays reflect as if it came there. So, important ray number one, a light ray traveling parallel to the principal axis, diverges and reflects away as if it came from the virtual focal point. Parallel light ray hits the mirror, reflects as if it came from the virtual focal point. Now, just like before, if I command this ray to turn around and go back in reverse, the same holds true. And it brings us to important ray number two. So if you have a light ray that's headed, shot like you're shooting it in, as if it could go into the mirror and hit the focal point. A light ray headed towards the mirror at an angle, so it's like headed right towards the focal point. When it hits that mirror, how's it going to bounce? It's going to obey the law of reflection and bounce back parallel to the principal axis. Just like reversing the first one. There's only one convex mirror case. Convex mirror. I can put the object anywhere I want out in front of the convex mirror. Remember, this is the side with the mirror. I'm going to make my object a little bit taller. First light ray, parallel to the principal axis. And this time it reflects up as if it came from the virtual focal point. Second light ray, leaving the head of the object, going straight towards the virtual focal point. So it's headed, like you know, it's aimed right towards the virtual focal point. That sucker is going to reflect back parallel to the principal axis. Hi, can I call you back in 10? Notice the reflected rays. Are they converging, parallel, or diverging? And what do diverging rays always form? Right. So if you put a screen out here, or out here, or out here, the light would just be blurry, getting farther and farther apart on that screen, like on the index card. You never get a real image. So scratch those lines. However, if you put your eye in the light and look into the mirror, if your eye catches those reflected rays, your eye will be faked out and think the light came from where those light rays intersect if you extend them backwards. Now careful, do you see this light right here? The extension backwards is right along the dotted line from the focal point. But for the other one, you see this is the reflected ray? It's not back along the dotted line. It's back parallel. So where would your eye be faked out and seeing? The light really came from the head of the object right here. But if you looked into that mirror, you would see the head right here. And if you played the same game for the feet would be found on the principal axis the same distance. So this here is your object, right there, womp, womp, womp. in there, that blue arrow, that's your image. And what can you say about that image, Dave?
Virtual.
Virtual. What else?
Smaller.
Smaller. Upright. Because the arrowhead is above the feet. Just like over here, the arrowhead is above the feet. So that's how you know it's upright.